All right, so we've been talking about, excuse me, talking about atoms, talking about the periodic table, and now we'll start to look at those atoms combining to form different types of compounds. Um, and then with this, when we're thinking about forming these substances, whether we're thinking about actually forming the bonds of the product, or even just if we're thinking about it in terms of a chemical reaction, breaking the bonds within the reactants first, all of those processes are going to involve the electrons. So the nucleus of these atoms are going to stay exactly the same. But in some cases, we're going to have atoms share electrons, and that'll give us one type of compound. So down here, those would be the covalent compounds. That's what I refer to them as. The textbook, I think, uses the term molecular compounds, but it means exactly the same. And with those ones, we'll have them sharing the electrons between the two atoms. That's what's actually holding them together. That's what's forming the bond. But what we're going to look at today, or in this video rather, is going to be the ionic compounds. And with these ones, as ionic compound would suggest, we're going to have ions involved. So an ion is just going to be a positive or a negative atom. So rather than being neutrally charged, we're going to have positive and negative pieces. So with that, that means one of those atoms is going to be gaining electrons. That'll be what gives us the negative ions. So if we're gaining electrons, we're gaining that additional negative charge. And then to specify the negative ions, we have the term anion. So the way that I remember is just kind of breaking that word down, a negative ion. And then if something's gaining electrons, something else has to be losing them. They can't just be popping up out of nowhere. So something has to be losing those. And if we're losing a negative charge, it's going to become positive. So with the positive ions, we also have a term to refer to those specifically. And that's just going to be the cations. And the way that I remember it is the T in the middle kind of just looks like a little plus sign. So with the ionic compounds, the thing actually holding those together is just going to be those opposite charges. So remember, opposite charges attract, like charges repel. So in this case, we'll have a positive and a negative piece, and those opposite charges are just going to bring these together. And then we can use the periodic table itself as a tool. So when we're looking at some of these groups, one of the bullet points I had on there was the number of valence electrons for those elements. That's why they behaved similarly. So for instance, all the halogens had 7 valence electrons. All of the alkaline earth metals had 2. But we can use the periodic table to determine what type of charge these elements are going to form. And essentially what's going to happen is they're going to either gain or lose electrons in order for them to get a electron configuration. So that'll be something we talk about later in the quarter, exactly how these electrons are set up. But essentially they want the same number of electrons as one of these noble gases. So these noble gases are the most stable. They have kind of the perfect setup in terms of their electrons. That's why they don't really do anything. They don't gain or lose electrons themselves. For the most part, just because they're already sort of happy with the number that they have. But we can use the periodic table to figure out how many do the other elements either need to gain or lose in order to get there. And with the nonmetals on the right, if you think about it, fluorine has 7, neon has 8 valence electrons. So fluorine wants to gain one more. Same thing, chlorine wants to become like argon. Bromine wants to become like krypton. So because they're just missing one electron, we're going to see these halogens are going to form a -1 charge. If we move over one group to the group 16 ones, oxygen now has to move 2 spots. So it has to gain 2 electrons. Same thing, sulfur. If it gains 2 electrons, now it's got the same electrons as argon. So that's why we're going to see group 16 will be -2. Similarly, group 15, -3. And then if we have carbon in an ionic compound, it would gain 4. So it would just be -4 in that case. But carbon is that's more rare to see than the other nonmetals here. But then with the metals on the left-hand side, it's the same idea. If we think about sodium, it could gain a bunch of electrons and then become like argon. But it's going to be much easier if sodium just loses 1 electron and then becomes like neon, or potassium loses 1 and becomes like argon. So we're going to see the group 1 metals are always just going to give up a single valence electron. That's why they're always going to be +1 in a compound. And then group 2, those alkaline earth metals, same idea. It's just now they have to move an extra spot. So magnesium has to move 2 to get to neon. So it's going to lose both of those electrons. It's going to be +2. And the same thing with the rest of that group. With the transition metals, including some of the metals that are also down here at the bottom, that aren't technically transition metals, those can have multiple charges with the exception of these three here. So silver is always going to be +1, cadmium is always going to be +2, zinc will always be +2. But with the rest of them, we've got different charges, and we're only seeing a few of them listed here. But with it, we'll have a special process for kind of handling those ones. So if we look at this one, a couple questions. We want to figure out just if these elements were to form an ionic compound, which are going to be positive, which are going to be negative, and then exactly what the charges are going to be there. So again, we can use the periodic table, just see how far they need to move. So in the case of magnesium and nitrogen, again, magnesium's group 2, it's got to move over 2. Nitrogen, group 15, needs to move over 3. So those are just the charges we would have there. And then aluminum and carbon, same idea. It's just aluminum in this case. We can kind of ignore this big stretch here. But if aluminum loses 1, now it's like magnesium. Loses a second, it's like sodium. And then it loses a third. Now it's similar to neon. So that's why aluminum would be +3. And then the carbon we talked about going to be -4. And ultimately what we'll be able to do is then use this information to figure out what that formula is actually going to be. But with those elements by themselves, those are monatomic ions because we just have that one thing with a charge. So an oxygen with a -2, sodium with a +1, aluminum with a +3. What we'll also see is just polyatomic ions. And these are going to be similar in the fact that we'll still have a positive or negative charge. But rather than having that charge localized on a single atom, now it's going to be spread around a collection. So if you look at OH- here, so oxygen and a hydrogen with a -1 charge, that -1 charge is over this entire thing. And then similarly with ammonia, NH4+, we've got a nitrogen with 4 hydrogens on the outside, and then that entire substance is +1. So with these polyatomic ions, we haven't talked about them yet, but the covalent bonds, when we actually share electrons, we have covalent bonds between these atoms, but then it's considered a polyatomic ion because the entire thing has a charge here. And with these polyatomic ions, there's a whole bunch of them. So you can see them here. With it, you're not going to have to memorize these. There is going to be a table that I'll give you that you can use for quizzes and tests and homework and stuff, because I don't think it's useful to have these memorized. But again, you can see in each of these cases, we've got a collection of atoms that have some charge overall. So that's why we're referring to them as polyatomic, multiple atoms together. And then the ion piece is just because they are still positive or negative. And with some of them, how do I want to go through this? So if you look at the left-hand side here, these are just the monatomic ions. So just chlorine or bromine, iodine, sulfide, nitrogen. So you can see in each case, all we did to the name of this is change the ending to IDE. So that IDE tells us this is the negative ion. But with the polyatomic ions, we've got what are known as oxyanions. So those are going to be polyatomic ions that contain oxygen. And then since it's an anion, you can see all of these are negative. There's going to be kind of a system we can use to kind of name sort of a series of oxyanions. So if you look here by series, I mean, we've got chlorine all the way across with 1, 2, 3, or 4 oxygens. Same thing, bromine, iodine is similar, sulfur and nitrogen. And with it, the ending, as well as the presence of a prefix, can tell us how many there are. Unfortunately, there's no set system. So if you look at this table here, you can see chlorate, bromate, iodate, and nitrate all have 3 oxygens, but then the sulfur has 4. So unfortunately, the ATE ending doesn't automatically mean 3 oxygens. But if we know what the 8 version of these ions are, and again, you won't have to memorize this, but just so we can kind of see the relationship, if we know what the 8 version of this polyatomic ion is, the ite version, so just changing that A to an I at the end, is just going to be 1 less oxygen. And then if we go 1 fewer, now we've got that same ending, but we've got a prefix there. So if you think about hypoglycemia, hypo just means less than. So hypochlorite just means 1 less oxygen than chlorite, which has 1 less oxygen than chlorate. And then if we have an additional oxygen still, you can think about the prefix per, so perchlorate. And really that's sort of shortening hyper. So if you think about hyperglycemia, too much sugar, a hyperactive kid, kid with too much energy. So this perchlorate, that per is just representing an additional oxygen there. But like I said, there's no set system, just because you can see sulfate has 4 oxygens, while the rest of the ATEs have 3. But if we do know one of them, we can use the system here to figure out what those other formulas are going to be. And that's what we're showing here. But with these compounds, the reason we've got the different types of compounds, just the types of bonds that are going to form them. So with the ionic bonds, remember it's positive and negative. We've got the cation and anion, and those opposite charges are going to hold them together. And then with the covalent bond, instead of having electrons fully move from one to another, so that's what's causing the positive and the negative charges, the transfer of electrons there. But with the covalent bonds, we're just going to be sharing electrons between them. And that'll be a little different. We'll see that in the next video. But with the ionic ones, just a simple one. So sodium chloride, probably the most common ionic substance. And with it, I should also mention, I think I talked about this in chapter 1, where we're looking at pure substances versus mixtures. The reason we consider compounds to be pure substances is, one, it's always going to be exactly the same thing. So with sodium chloride, we'll always have exactly 1 sodium with 1 chlorine. But also because when we form these compounds, the elements themselves are no longer going to retain all of their individual properties. So with sodium chlorine, sodium, extremely reactive metal, chlorine, extremely toxic gas. But then when we take them together and combine them, we just get table salt. So with the exception of high blood pressure, not really anything too problematic. But with these ionic compounds, like I said, the thing holding them together is going to be that positive and the negative charge. So with sodium chlorine, we can see sodium has 1 extra electron that it basically wants to get rid of. And then chlorine is missing 1, so it wants to gain 1 more. So we just see that transfer occur. And then when we do that, we don't change anything about these nuclei. So sodium still has 11 protons, but now it's only got 10 electrons, so it's got a positive. Chlorine still has 17 protons, but now it's got an 18th electron, so we've got the negative there. So that's what's going to be holding these together. And then with this, we've already seen kind of the charge that we can use to identify these, or at least based on the location we can use to identify the charge. Now we're going to look at how we can actually piece that together and get the formula. And there's a couple of different ways you can do it. So if we look at the 2 examples at the bottom, in each case we're having lithium as the metallic part. So lithium group 1, going to lose that electron, become like helium. So it's going to become positive 1. And then sulfur and chlorine just needs to move over 1. Sulfur needs to move over 2. So that's why we've got -1, -2 there. When the charges are the exact same, but just opposite sign, so in the case of lithium and chlorine, the formula of that ionic compound is just going to be 1 to 1. We need just 1 lithium to balance out that chlorine. But in the case where there's different charges, we've got to think about what ratio we need them in, because these are going to be neutral when they're in the compound form. So if you think about sulfur, needs to gain 2 electrons. But if lithium can only lose 1, we're going to need a second lithium there. So the formula would just be Li2S. And if we look at something similar with oxygen, we can see what's known as the crisscross method. So in this case, what you can do is take the charge. So write out the ions themselves, include the charge for both. And then you don't need to do it with the positive or the negative sign, but take that number and just crisscross it. So bring it down as the subscript for the other piece. And that's how we can get the formula for that ionic substance. And again, with this, you can always check to make sure that what you have is correct. Because if we think about it, each of these lithium are +1, but we've got 2 of them. So that's a +2 charge overall. And then the oxygen, we only have a single one, but it's -2. So we've got a +2 from the lithiums. We've got a -2 from the lone oxygen. So we've got that balance of charge. And that's why this is a neutral molecule, neutral compound. And then with this also note, once we write it as the molecular or the ionic formula, we no longer include the charges for those ions. So once we write this as one whole substance rather than the individual ions, we no longer need to include the plus or the -2 for oxygen, just because the compound as a whole is neutral. And then with these ionic compounds, we'll talk about some of these properties in some of the later chapters. So with like enthalpy of fusion and vaporization, we'll look at that when we discuss thermochemistry. Essentially what that means though, is these ionic substances require a lot of energy in order to melt it in the case of fusion, or turn it into a gas in the case of vaporization, so boil it essentially. And that should make sense because if you think about, again, just sodium chloride, you can turn your oven up as high as you want, throw in some food with some salt on it, and then when you take it out, that salt's still just going to be salt. It's not going to melt at all, just because it's going to take so much energy in order to actually have those phase changes occur with these ionic substances. And then soluble in water, conduct electricity in solution. Oops. Okay, sorry about that. Forgot what I was saying. I think I was talking about the solubility, but if you think about salt water, for instance, that salt dissolves well in water. And then if you've ever heard about electrolytes, what it's just referring to is essentially these ions dissolving in solution and then being able to conduct electricity. But that'll be something that we cover later on. And then just because we've got a picture here and it talks about crystals with these ionic substances, depending on the charge of those ions, depending on the size of those ions, we actually form different crystal structures. And if you take inorganic chemistry, I think you would probably go into something like that in terms of the exact shape of those different crystals. But if we look at this one now, the gemstone sapphire, you can see just the little gem in the middle there, got kind of that blue tint to it, is mostly aluminum and oxygen. So we've got an ionic compound containing those two. The thing that actually gives it the blue color is just going to be small amounts of the iron and titanium. But with it, if we want to figure out what the formula for this aluminum and oxygen compound would be, we have to first identify what the ions are. So in this case, we're given that information. But then with it, we can then think about the crisscross method, how many of them are going to need to combine. So if we take the 2 down, that'll give us Al2. So I can do, so if we do the crisscross method, we take this 2, bring it down to the other side, so that'd be our subscript for the aluminum, and then do the same thing with 3 down for oxygen. So we would see aluminum oxide, the formula for it, just going to be Al2O3. And then again, you can check to make sure that this is balanced in terms of charge, because if we've got 2 aluminums that are each +3, that'll give us a +6 charge overall from the 2 metals. And then if we've got 3 oxygens that are each -2, that'll be -6. So we can always check to make sure that this is correct. And then for the next one, we can do kind of the same thing. With the sodium, we're going to bring down that 2 from sulfur, Na2. And then we're going to have this +1. It's just +1 though, so we don't need to write the 1 as the subscript. So we can just have Na2S. And then again, sulfur is -2. Each of these sodiums are +1. So we've got a +2 overall from each from the sodiums combined, and then just a -2 from that lone sulfur. And then with this one, going to be kind of the same idea. It's just in this case, we've got a polyatomic ion. But if we weren't told the ions themselves, if we were told we have calcium with dihydrogen phosphate, calcium, we can look at our periodic table, see that it's group 2, is always going to have a +2 charge then. And then with the dihydrogen phosphate, okay, so good. So I knocked on the door again. But with calcium, group 2 always going to be +2. The dihydrogen phosphate, that would be on the polyatomic ion list if we were going to use it, so you don't have to memorize this piece of it. But we can just write out both of those ions, Ca2+, H2PO4-, and then again, we're going to do the crisscross method. So if we focus on this negative one first, we're just going to bring down that 1. So we would just have Ca. And then with the 2, we're going to bring this down. But when we do that, we want to say that we've got 2 of these dihydrogen phosphates. So we've got 2 of this entire unit. We're just going to have that in parentheses then. So H2PO4. And then to say we've got 2 of that entire thing, we now put the 2 there. So the parentheses here, kind of like in math class, you've got a number on the outside of the parenthesis, gets distributed to everything on the inside. So now this is saying we have 4 hydrogens, we've got 2 phosphorus, and we've got 8 oxygens. But we want to keep it as this sort of format rather than just writing that out, because this tells us we've got 2 of those dihydrogen phosphates rather than just kind of a random collection of 4 hydrogens and 2 phosphorus, 8 oxygens. So with the next one, if you want to practice that, you can, and just pause the video. But in this case, we're looking at lithium combining with a peroxide ion. So if we look at our periodic table, we can see lithium, Li, group 1. So it's just going to have a positive 1 charge. And then the peroxide ion looks a little bit different than some polyatomic ions, because this one is just the same element, but it's still a polyatomic ion because it's 2 oxygen atoms together with a -2 charge overall. So we'll have Li2, O2 minus. And again, doing the crisscross method, bring down the 2 from the peroxide, make that our lithium charge. And then with the oxygen, we're bringing that 1 down. We don't need a parenthesis in this case, just because we have 1 of that peroxide ion. If we had something with a positive 3 charge, then we'd want to put the O2 in parenthesis and the 3 on the outside. But in this case, since it's just a single one of those polyatomic peroxides, we can just keep it as is. Oops, and then let me erase this quick. It's always good when I get the correct answer at the end. Okay, and then with these ionic compounds, even if you're not familiar with them, they are in a ton of different products that we use fairly often. So you can see sodium hydroxide, we'll use that one in the lab quite often just because it's kind of the most common base. But if you ever use drain cleaner, likely was sodium hydroxide. And acids, we'll have a lab where we look at a couple different antacids, see how effective each of them are. But you can see we've got a couple different ionic substances that could be used for treating that stomach acid. Food additives, food preservatives, potassium iodide we talked about in terms of making sure that you're getting enough iodine in your diet. They add that to just table salt, sodium chloride, to make sure that you're getting that iodide. A lot of fluoride compounds are in toothpaste. Baking soda, for instance, is another one. And then just a whole bunch of other ones. So these are going to be things that if you look at the ingredient list for different household products, sometimes you'll see an ingredient list for food, but a lot of different products are going to contain these types of compounds. And then when we're looking at determining the name of an ionic compound, we're going to be looking at a couple different versions. But we're primarily going to, with the exception of when we've got a polyatomic ion, be looking at binary ionic compounds, meaning we've just got 2 different elements. With the polyatomic ions, it'll be actually kind of a little easier because we can just name it as is. But with these ionic ones, if you look at all these, we've got a metal with a nonmetal. And then if we look at the naming system with these ones, we can identify the process we use, because we've got sodium chloride, potassium bromide, calcium iodide, magnesium nitride, whatever it is. So with the metal, we're just going to keep that name exactly as it is. So you don't have to change anything about that first element. But then with the second one, what we're going to do is just drop the ending and change it to IDE. So that's why you can see chlorine becomes chloride, bromine becomes bromide, oxygen becomes oxide, phosphorus, phosphide, carbon, carbide. But we're not going to change anything about the metal name. And with this, we don't have to specify anything about the number of these ions we're going to have. So if you think about like carbon dioxide versus carbon monoxide, we're actually specifying how many oxygen are in that formula. Because with the covalent compounds, we can actually have different ratios of the same elements. But with these ones, since it's always going to be a positive and a negative attracting, and because we're always going to have the same charge on these pieces, we're always going to have them in the exact same ratio. So by saying calcium iodide, we can always just, even if you don't know CaI2, you can always look at your periodic table, see calcium is going to be +2, iodine is going to be -1. So we're going to need them in that exact ratio in order to get a neutral compound. Same thing, magnesium nitride, we're always going to have 3 magnesium for every 2 nitrogen. There will be some examples with the elements in the middle where they can have those different charges. So like iron can be +2 or +3. In that case, we'll have one additional step, but we'll talk about that in a little bit. And then, like I said, the polyatomic ions is going to be the only case where we have more than 2 elements. And with these ones, it's almost a little bit simpler if we're going from the formula to the name, because in that case, we can just look at our polyatomic ion list, look to see what that ion is, and then just throw that name in exactly as it is. So you don't have to change anything about these. So C2H3O2 is the acetate ion. So when we've got it with potassium, just potassium acetate. NH4 is ammonium, so we don't have to change anything about those. If chlorine is with that ammonium, though, we're still going to change the ending of that one. But you can see phosphate, PO4, don't have to change anything about that. Same thing, sulfate. So with the polyatomic ions, it's still the same idea, positive and negative pieces. It's just when we go to name it, that polyatomic ion, we can just keep that name exactly as it is. But like I mentioned, the transition metals and then a few other ones like tin and lead can have multiple charges. So if we just say like iron chloride, we know what 2 elements we're dealing with, but because we can have different charges on iron, we can have a different ratio here. Same thing, mercury oxide, tin fluoride. Those tell us what elements we have, but we don't know for certain which ratio we have them in. So we've actually got to do a little bit of work to figure out what the ion is, so we can then include that charge in the Roman numerals. So just looking at these ones, and we'll go through this process in a moment, but just looking at these ones, note that the Roman numeral doesn't match the number of iron we have, or the Roman numeral doesn't match the number of mercury. Same thing, doesn't match the number of tin, because these Roman numerals are just specifying the charge on these different ions. So iron 2 versus iron 3 is just iron's going to have a +2 charge in the first one and a +3 in the second one, where each of these mercury is going to be +1, while this lone mercury is going to be +2. And then the same thing, 2 and 4 here. Tin 2 fluoride is going to be a tin with a +2 charge. Tin 4 fluoride is going to be a tin with a +4. And like I said, we'll see exactly how we can kind of go through and get those. But just also know, if you ever see I don't think the textbook really uses it. I'm never going to use it, but there is an old system for naming ionic compounds with these types of metals in it. And with it, instead of saying like iron 2 or iron 3, we would say ferrous or ferric chloride, because the OUS or the IC ending on those refer to those specific charges. But with it, we're going to use the IUPAC system, which is the Roman numerals like we see here. And then there's another type of ionic compound where the ionic piece is still the same. So if we look at this one at the bottom, CuSO4, still copper 2 sulfate, or MgCO3. So we've got polyatomic ions in each of these, but that would just be magnesium carbonate. So if we're naming it, we would still treat that exactly the same. But we've got what are known as hydrates, which, as it says here, just the salt. So an ionic compound is just also known as a salt. Sodium chloride has kind of monopolized that in terms of like general speech. But in chemistry, a salt is just going to refer to a soluble ionic substance. And what we can see with these ionic compounds is sometimes they essentially just get surrounded by water molecules. So even as a solid, in this case, we'd have like copper sulfate, that ionic molecule, surrounded by 5 water molecules, or in the case of the magnesium one, we'd have that magnesium carbonate surrounded by 10 water molecules. Oh, I didn't realize this image already had a mouse there. So with that piece of it, we still treat it the same. And then just to signify that we do have those water molecules associated with them, we just have the hydrate piece at the end. And then to tell us how many of those water molecules we have, we just have the prefixes here. So on that polyatomic ion list, you'll also have these prefixes given to you, so you don't have to memorize them. Some of them, like mono, di, tri, fairly familiar. Penta, hexa, hepta, octa, just thinking about like hexagon represents 6. But you don't have to memorize what these are going to be. But just note with these formulas, and we had the lab during the second or the third week of classes focusing on this, or maybe it was the fourth even. But we have the formula here. So with it, just note we put a dot in between those pieces, showing that they're not kind of the same formula, but showing that they're still related. Whoops. And with it, we'll see in chapter 3, we'll look at kind of the percentage of water in these compounds is going to be a type of calculation that we're going to be doing. But if you want to practice here and think about how we can go from actually with this one, we should go through it together. So looking at these ones, these are going to be, for the most part, there's going to be one of them that the Roman numerals aren't necessary for, but for most of them, that's going to be the case. So actually, let me do this so I can actually type. It'll be a little bit cleaner than when I try to draw. But looking at these, we've got iron, but iron's a transition metal, so it's in the middle of the periodic table. So we don't know for certain what that charge is going to be. And we've got 2 of them. So what we can do is kind of set up a algebraic equation to determine what these charges are going to be. Because if we look at it, we know it's going to be iron sulfide, or if we look at the next one, copper selenide, gallium nitride, with the SO4, that's going to be a polyatomic ion, so that'll be magnesium sulfate. And then we've got the hydrate there, so heptahydrate or titanium sulfate. But with everything with the exception of magnesium, we need the Roman numerals here. Magnesium just group 2, so we always know it's going to be a positive 2 charge, so we don't need to specify it. But with iron or copper or gallium or titanium, we can have different charges. So we've got to specify which version of those metals we have. And in order to determine what that's going to be, we can set up a algebraic equation like this. So this is showing us we've got 2 of the irons plus 3 of the sulfurs. And then I have this set equal to 0 because it's neutral overall. So we're going to have a positive, some positive charge on iron. We don't know yet. Some negative charge on sulfur. But with the sulfur, we can use the periodic table to determine what that charge is going to be. We know it's going to be -2. So then if we go through, that means we're going to have 2 irons. So I'm just using the symbol as a sort of a variable for the charge itself. But 2 times negative, or 3 times -2 rather, is going to give us -6. And then that's going to be equal to 0 still. So we can continue to just isolate that variable. So 2Fe is equal now to just 6. And we're going to see Fe in this case is going to be equal to +3. And again, the reason we can do this is because we know that sulfur, based on the group of the periodic table, needs to gain 2 more electrons. So that's why we have the -2 here. If there was an element that we couldn't know the charge of in the place of sulfur, then we wouldn't be able to do it. Similarly with copper, we could do kind of the same thing. In this case, we only have 1 of each, so we can just do Cu for copper plus Se. But selenium, just like the sulfur, is going to be in that 16th group, so it's going to have a negative charge. So in this case, what we're going to see is copper is just going to be 0. Like I said, with the magnesium for D, we don't need to determine that one. We know it's +2. So if you wanted to practice with C and E, see if you can identify what those charges are, go ahead. This one we can kind of do the same as we did here. With the titanium sulfate, we need to know what the charge on that polyatomic ion is. So if you don't have the polyatomic ion list with you, you may not have that memorized. But if we think about it, magnesium's +2. So this SO4 has to be -2. And that'll be the same charge we have here. It's just now with this one, we've got multiple. So if you feel comfortable and want to practice with that, go ahead. If you want to see me kind of work through it more, we can do that as well. So with the gallium one, Ga plus N, again, equal to 0 because it's neutral overall. Those positive and negative pieces have to balance out. And then with nitrogen, now it's in group 15. So we've got to move one group further this time. So we need to get a third electron. That's why we have a -3. But we just have one at each of those, like we did with the copper one. So it makes it a little bit easier. And I do not know why I didn't correct this. So copper won't be equal to 0. It'll be equal to +2, just to balance out that -2 from the selenium. And then, like I said, magnesium, we don't need to do any math there. But with the titanium, set up the algebraic equation. So 2 titanium plus 3. And then in this case, I'm just going to do, I'll just do S for the sulfate, just so I don't have to write out SO4. But it's going to be equal to 0. And then remember, when we've got these parentheses, we have the number on the outside. We've got that many of that thing. So in this case, we've got 3 of the sulfates. And like I said, we can get this from the polyatomic ion list, so you don't have to memorize this one. We don't have to look at the periodic table, but sulfate's always going to be -2. So in this case, we've got to do a little bit more math like we did for the first one, but 2 titaniums is going to be equal to -6. And we still have it equal to 0. So just like the first one, 2 titanium, we can subtract, or we can add that 6 to both sides now. We get 2 titanium is equal to 6, which means each of those titaniums individually is going to have a +3 charge. So with it, it's just a little bit of a puzzle piece in terms of finding out what information do we know, what information are we looking for, what can we get from the periodic table. But with the magnesium one, just to go back to that one, like I said, magnesium's always +2. So the sulfate as a whole is going to be -2. That's why it's balanced. But if we have a hydrate, just note that the water molecule itself, all of those water molecules, doesn't matter if we have 2, if we have 7, if we have however many, the water molecules themselves are neutral. So that's not going to affect the charge at all. That's not going to affect this ionic piece. It's just basically whatever this ionic piece is now surrounded by those water molecules. Okay. So then when we go to name them, we don't want to just say iron sulfide or copper selenide, gallium nitride. Now we want to include the charge we determined for those 4. So that's why when we look at the answer key here, we've got iron 3 sulfide, and we can go back, double check that makes sense. Each of these irons is +3, so that gives us a +6 from the iron overall. Each sulfur is -2, so that gives us a -6. We have that balance. Copper 2 selenide, copper's +2, selenium's -2, balanced. Gallium 3 nitride, again, +3, -3. We still have that balance. With the magnesium one, we can just say magnesium because it's always going to be +2. But in this case, we've got the water molecules with it, so we don't want to just say magnesium sulfate. We want to say magnesium sulfate heptahydrate. And then with the final one, again, titanium sulfate would tell us we've got titanium with some amount of sulfate, some amount of those SO4. But by telling us we've got titanium 3 sulfate, we can know that it's this exact formula. And again, we can double check. Each titanium is +3. Got 2 of them though, so it's +6. Each sulfate is -2, but we've got 3 of them, so we've got the -6 charge. So with these ones, you can always double check just to make sure that those positive and negative ions all balance out. Okay, so if you want to try with this one, pause the video. In this case, we're just going in the reverse direction. But what I'm going to do again is just send this to the back, just so we can work through these ones. So if you do feel comfortable going in this reverse direction now, feel free to pause it, try it on your own. Just skip ahead, see what the answers are. But with these ones, kind of similar to what we did before, it's just now we've got, and these ones actually with the name to the formula for these transition metals may actually be easier because in this case, we don't need to look at our periodic table. We know exactly what that charge is going to be. So we're going to have selenium with or chromium, excuse me, with a +3 charge. Actually, I'll do this. Whatever. So just make it a superscript. And then with I'm going to skip ahead here, just so it doesn't all get messed up. But then I'll do superscript as well for the charge on this phosphorus. And if we look at the periodic table for the phosphorus, going to be in the 15th group. So it's going to be a -3 charge. So with this one, we could do the crisscross method, but remember, if you do that, you're going to wind up with CR3, P3. We want to reduce those subscripts as much as possible. So we just have CRP. And remember with it, when we've got equal charges but opposite sign, we can just have those in a 1-to-1 ratio. So for chromium 3 phosphide, we would just have CRP. Lift this one up. Yeah. Then with the next one, same idea. HG. If I can just copy this and just change that's not what I wanted. All right. So with it, just so I don't have to keep doing the subscript each time, or the superscript rather, we're just going to do this. Mercury 2 sulfide, mercury with a +2 charge, and then sulfur, group 16, is going to be a -2. So in this case, we're just going to have HGS. So again, we've got equal but opposite charges there. So we just need one of each of those ions in order to balance out the other. So that's why we just have HGS, or we just have CRP for the first one. Okay, with this one, I'm going to be a little bit more. So with this one, manganese, I'm going to change that symbol to Mn, and then it's manganese 2. So we've got a +2 charge there. The phosphate piece, this one will need to do a little bit work. Phosphate is going to be, if you don't have the polyatomic ion list with you, is just going to be PO4 with a -3 charge. So in this case, when we do the crisscross method, when we think about how many of these these ions we need, one other way you could do it is just think about what's the smallest common factor that both of these charges will go into. 2 and 3, so it's going to be 6. So we're going to need ultimately a +6 charge from the metal, -6 charge from the phosphate. Or if we do the crisscross method, we'll wind up at the same point. But we're essentially going to be bringing down that 3 for manganese. We're going to then put the PO4 in parentheses. So I'll do the subscripts in a second. But now we're going to bring the 2 down to the phosphate. And when we change these and make them actually correct, when we change them to the subscripts, there's probably a shortcut on the keyboard I could have done to make this a little smoother, but I do not know what that is. But now when we look at it, it's telling us we've got 3 manganese, each are +2. So again, +6 charge coming from there. And now it's saying we've got PO4 in parentheses with a 2 on the outside. So we've got 2 of this PO4. We've got 2 of these -3 charges. So now we've got that -6 to balance it out. Whoops. Oops, it's still subscript. Okay. And then we see the fourth one. In this case, we've got copper, so Cu, and then it tells us copper 1. So we've just got a positive charge there. In this case, we don't have phosphorus, so we've got oxygen. So now with phosphorus, it was -3 because it was in the 15th group. Oxygen is just in the 16th though, so it only needs to gain 2 electrons rather than 3. So with this one, if we think about it, oxygen going to gain 2 electrons. Copper though is only giving up 1. So if oxygen needs to gain a second one, we'll need 2 of those coppers present. And again, you do the crisscross method, wind up at the same spot. So just Cu2O. And then with the final one here, let me do that. So again, with this piece, the dihydrate isn't going to affect the formula for the ionic part. So we can kind of just worry about that at the end. But we do have iron, so we'll change that to Fe. And it's still iron 3, so we'll have that same +3 charge. With the non-metal portion, with that anion, we're going to have chlorine, but it's a halogen, group 17, only needs to gain 1 more electron. So we're just going to have Fe3+, and then a negative chlorine. So when we get the actual formula, we're going to need 3 of those chlorines. So okay, if you think about it in this case, iron's giving away 3 electrons. Chlorine, though, can only take 1. So we still have 2 other electrons there. That means we need 2 more of the chlorine. So we're going to have 3 in total. And then with it, let's see. I'll just do that. So again, normally it's a dot, but just to make it a little easier on myself with this keyboard, I'll just do the little asterisk thing. But we've got iron 3 chloride hydrate, so we're going to have water with it. So it's not just going to be that ionic compound. Now we're going to have it surrounded by those water molecules. But this tells us dihydrate, so we're going to have 2 of those water molecules with it. And that's why if we go to this next slide, we see that exact same thing. Hopefully those are the same formula I had there. CRP, HGS, 3 manganese with 2 phosphates, 2 coppers with an oxygen, and then the iron with 3 chlorines, and then the 2 waters attached. So again, if we're just kind of thinking about these as positive and negative ions, thinking about needing to balance them out, the transition metals are a little bit easier in some sense because they give us the charge directly for that metal. With the group 1 and 2, of course, we know what those charges are. It's just not explicitly written there. But it's going to be that same process either way. And then with it, that'll be the end of the ionic section. So the next one will just look at the covalent compounds, and that'll wrap up chapter 2.